Hi guys, welcome to the channel Eat Code and Sleep. Okay, today's LeetCode problem is house robber. Okay, so this is a this is another recursive and DP problem here. So we are getting a lot of problems from recursion here. So it's an well and good, right? So it will be a very good practice for us, right? To practice DP and practice recursion, right? So let us quickly dive into the problem. And so, first of all, we will see what are the companies asked these questions. Okay, how many companies have asked this type of question? Okay, so if you see, Cisco has asked 5 times. Okay, Amazon, Google, Apple, Bloomberg, Adobe, Infosys, Microsoft, Walmart, Databricks, TikTok, Qualtrics, S&M, Facebook, ByteDance, Yahoo, Flipkart, Paytm, Goldman Sachs, and Oracle, and these many companies have asked this question. Okay, and so let us quickly dive into the problem here. Okay, so you are a professional robber planning to rob houses along a street. Okay, you are a professional robber, it seems, and planning to rob houses along a street. So basically, the houses will be in along a street in a straight line, and we have to rob those houses. Okay, so each house has a certain amount of money stashed. Okay, each house will have some money. Okay, will have some money in their home, and it will be stashed. Okay, so the only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Okay, if two houses, okay, so if two adjacent houses are robbed, then automatically you will be caught. Okay, so we have to make sure that we don't rob two adjacent houses here. Okay, so well and good. So now let us read the input we have given. Okay, so given an integer array nums representing the amount of money of each house. Okay, there are n houses, so and each house is having this much of amount in array nums. Okay, so return the maximum amount of money you can rob tonight without alerting the police. Okay, so you have to rob from all the houses, from not from the all houses. You have to rob the street within tonight without alerting the police. That means without getting caught. Okay, so let us quickly observe the test case here. So this is a test case 1231 and 4. 4 is the output here. Okay, so house 1, so Rob, what he did is he robbed house 1 here, and then robbed house 3 here. So the total will be how much? So the total will be 4 here, right? So in what cases we can rob here? So we should not rob this and this at a time, right? So if we rob this, we should not rob this, right? Right, that is true, right? And if we rob this, we have to not rob this and this, right? So that is true, right? These are the adjacent houses which are having for second house, right? So if at all we rob a house, we need to not rob the adjacent houses. This is the constant given here. So what are the other other patterns we can rob? So if we rob here, we cannot rob here, right? So we can rob here, so we will rob here. So 1 plus 3 will be 4. So if we rob here, we cannot rob here. So we will ignore this and move out of the street. So this is how the maximum is gotten. So another observation. So if we don't rob this house, we can rob number 2, right? Second house, right? So we will rob second house. So if we rob second house, we need to not rob third house, right? So we will skip this and we will rob this fourth house because it is not adjacent, right? So so what is the pattern? Second house can be robbed and fourth house can be robbed here. So what will be the output here? 2 plus 1, which is 3. But the maximum was 4 here. So we'll be returning 4 in this case. Okay. So we'll observe another test case here. Okay. So 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 explanation. Rob. House 1 was robbed. Okay. And robbed house 3. okay, and robbed fifth house. So he got an answer of 12 here. So he robbed this house, and this house. And if you see, they are not adjacent to each other. Okay, we will see another case here. Okay, so the rob said we don't rob this house, and we will move to next house. Okay, so he didn't rob number first house, and he moved to second house. So he is willing to rob this house because he didn't rob the adjacent houses, not yet, right? So he can rob this second house, right? So he will rob this second house. So he robbed the second house and moved further and came to the third house. He cannot rob third house, right? Because he robbed the adjacent house, second house, right? So he will move further, he will go to fourth house, and fourth house can be robbed now because the adjacent houses are not robbed. So he will rob this fourth house. So what is the output till now? 7 plus 3, that is 10. So he will go further and fifth house. He can't rob fifth house, right? Because if he rob that fifth house, he will automatically get caught, right? So he will skip this fifth house and move out of the top street. So what is the output now? 7 plus 3 is 10, which is lesser than 12. So what is the pattern here we need to rob? In what pattern we need to rob? First house should be robbed, and third house should be robbed, and fifth house should be robbed. This is the pattern to get the maximum profit here. So there are patterns in this sum, right? So there are patterns in this problem, right? So and another observation is we have to get the maximum amount of money. So as I said, these type of problems can be solved in recursion by using recursion. So we'll try to solve this recursion. Okay. So what are the cases we have here? So either we can rob this house, or else we cannot rob this house, right? We can rob this house, or we cannot rob this house, right? So these are the two conditions we need to remember. So we'll quickly try to solve the recursive approach here. Okay, so I will call for a recursive function that is solve, and I will pass the index where I need to start. I will always start from first house. So and I will also pass the array here. Okay, now I will create a public function here. So it will return integer because as he is asking for the maximum profit, profit can be in number value only, right? So if I will return the integer, okay, and I will call the function here. So I will be the index of my house, and nums will be the money. Okay. So now, in what cases I cannot rob here? Okay. In what cases I cannot rob? Either if the two adjacent houses are robbed, or else if it is out of bounds, right? When it can be out of bounds? When if I is greater than or equal to n, then I can say that I cannot do the robbing and I'm out of the street, right? So here, what should I return? I'll return 0 here. In this case, I'll return 0. So now I have come to the function. I'm not in the outer bound case. I'm not out of the street. I'm in the street and have to rob the houses. So now I will rob the house. Okay. So I will rob. So I will rob and I will. So if I rob, I need to include that stashed amount, right, uh, into my bag, right? So I will add that amount from that nums array, and I will add it to my bag. Okay. So plus, and I will call for the another function here. So if I stashed this house, I should not start the adjacent house, right? So I will not call for the adjacent house, and I will call for the other house, that is I plus 2 house. Okay. So I plus 1 is adjacent house, I plus 2 is not adjacent house, right? So I will call for the adjacent house, I plus 2. Okay, this is how I will rob, and I will not call the adjacent house. Okay, and I am making sure that I am not getting caught here. Okay, if I am not willing to if I am not willing to rob here, okay, I will not rob this house. So this house has a okay, whatever the case is, I don't want to rob this house. So what should I do? I should not include that money into my bag, right? Don't rob. So I should not include that rob, right? So can I move to the next house? Yes, I can move because I didn't rob this house. So it is no. Okay, I can move safely here. Yes, I didn't rob the initial house, so I can move to the next house. earlier we robbed that house, so we have to not move to that. We don't want to move to that and move to the adjacent one, and we have moved to the further houses, right? So, but here in this case, we don't want, we want to not rob this house, so we can move to the next house, right? So we don't want to rob, so I'll move to the next house, which is high plus one, and nums. So at last, what will be the maximum profit here? Maximum of rob and don't rob, right? That's it. So what will be the profit here? Return dot math dot max of rob comma don't rob. That's it. Here's the solution here, and let us try to run the solution here. So here n is not declared, so we will declare it as in nums dot length. Okay. See, we have passed the solution, but if you observe the So but if you observe the test cases, there are 100, and we are using two cases, right? So it will be 2 to the power of 100, which is more than the time complexity, right? It will be hell lot of time complexity, right? So we have to optimize this solution. What will be the optimization of recursive solution? It will be a DP. So we will be using a dynamic programming approach here. So before going to dynamic programming approach, so how we can apply dynamic programming, we will visualize by a recursive tree here. Okay, so we will see the recursive tree of this recursive solution here. Okay, so I have drawn the recursive tree of this input here. Okay, for this first uh, input, I have drawn the recursive tree here. So let us visualize this input here. Okay, the left condition will be the robbed condition, and the right condition will be the didn't drop the condition, didn't drop case. Okay, rob case and not didn't drop case, right? So the left will be the rob case, and right will be the didn't drop case. Okay, so so I am at a 0 comma, so I am at the first house. Okay, 0 means first house, right? And the value of the first house is 1. Okay, so now what will I do? I need to call, I want to rob this house, right? So I will rob this house, and I will not move to the adjacent house, and I will move to the adjacent of adjacent house. Okay, I'll move to the this index, second index, that will be second index, right? So this I will move to here. Okay, so I will rob this house, and I will move to second index. Okay, from here. So from here, if I want to rob this house, I can rob this house, right? Because it is not adjacent to any robbed houses, right? So I can rob this house. So I want to rob this house, so I will rob this house. Okay, so from here, where I can move, I will move to, I cannot, if I rob this house, I cannot move to this house, right? So I'll move to the fourth house, which is out of bound condition. So from here, what we will return? So let us copy this function. Okay, and let us zoom in a little bit, and more zoom in. Okay, I think it is not visible. Let us minimize little bit. Okay, and let us zoom it. Okay, so now, okay, now it is visible, right? So I am at this house, right? So I want to rob this house, so I will not move to the adjacent, adjacent house. If I rob this house, I know I should not move to the adjacent house. I should move to the adjacent house, right? So I'll move to the fourth house, which is out of bound condition. In out of bound condition, what we have to return here? We need to return 0 here. Okay, so what will be the value here? It will return 0. Okay, so this function will return 0 here. So after getting this function, we'll get here. So from this house, I don't want to, um, I will get to the second house, that is third house. So from here, I use this case called a robbing case, and I want to use the another case which is don't rob case. So I will check whether I can, if I don't rob, what will be the answer here. So okay, so I don't want to rob here, so I can move to the adjacent house. Right? If I don't want to rob, I can move to the adjacent house. So I'll move to the adjacent house here. That is fourth house. Okay. From here, if I want to rob this house, then where should I move? Oh, have to move to the adjacent. I have to not move to the adjacent house, right? So I'll move to the adjacent house. That is fifth house, which is not at all present. So I'll return here 0, which is sort of one condition, because I'll return 0 here. Okay, so I have written 0 here. So if I want to rob this house, so I'll go to this house and I will get a 0 here. So if I don't want to rob this house, so I'll not rob this house. Okay, so uh, so if I want to rob this house, 0 plus what will be the answer at the third index? From here I want to rob this house, right? So what will be the answer? 1, right? So 0 plus 1, it will be 1, right? So it will be 1. So if I don't want to rob this house, so I can go to the adjacent house, right? So if I go to the adjacent house, it will be the out of bound conditions, and it will be 0 here. Okay, so it will return 0. So what will be the maximum of these two? 1 will be the maximum, so I'll return 1 here. Okay, so this is the case for not robbing. So I will not include the value here. Okay, so this is the case for not for robbing, right? So I will include what I should need, what I should include, 0 plus 3 here, right? It will be equal to 3. So this is the robbing condition. This is the condition for not robbing, right? What is the maximum here? I think the maximum will be 3, right? So I'll return 3 here. So this will be 3 plus, if I rob this, this will I should rob this, right? So what will be the condition? 3 plus 1. So which is 4 here, right? So we got a condition as 4 here. So if I rob the first house, I got an answer as 4. So what? Let us check what will be the answer when we don't want to rob the first house. Okay, if we don't want to rob the first house, then we will go to the second house. So from here again, if we want to rob this house, then we will go to, if we want to rob this house, we cannot go to the adjacent house. We should go to the adjacent house. We'll come to the third index, right? So if you want to rob this house, we have to move to the adjacent house. So we'll rob this house and move to this house. This is the out of bound condition, and this will return 0 plus robbing condition, right? That will be 1 here. Okay, which is equal to 1. Okay, so and I don't want to rob the last house, and I want to move to the next house. So if I move to the next house, it will be out of condition and it will be 0. So what will be the maximum of 1 comma 0? 1. So I will be getting, what is the condition here? If I rob the last house only, I am getting a maximum value. So I will rob the last house and move to the, and I will rob the last house. Okay, so by robbing the last house, what was I getting? 1 I am getting, right? So 1 plus, what was the, if I rob if I rob what, if I rob second house, what will be the value here? 2. 1 plus 2, which is equal to 3 here. Okay, if I rob this house, this will be 3 here. Okay, and for by robbing the second house, I got an answer as 3 here. Okay, so what if I don't want to rob the second house? Okay, I don't want to rob the second house, and I will go to the next house, that is third house, right? So I'll go to the third house, which is this, right? So from here, where I can go, if I rob this, if I rob the third house, where I can go? I can go to the adjacent house, right? Which is equal to 0, right? Which is out of bounds. So I'll return 0 plus 3 here. equal to 3. Okay. If I want to rob the house, then I will get an answer as 3 here. If I want to rob the third house, then I will get an answer as 3. If I don't want to rob the house, don't want to rob the third house, then what will be the answer? Let us check. If I don't want to rob the house, then I can move to the fourth house. From fourth house, I will be moving to fifth house if I rob the condition. So here, what will be the answer? If we go to fifth house, it will be out of box condition. So from there, it will be written 0 and 1 here. So it will be equal to 1 if I rob, and if I don't rob, it will be 0, right? From if I rob the last house, then I will get 1. If I don't rob the last house, then I will get 0. So from what is the maximum here I'm getting? By robbing the house, right? So I'll return 1 here. Okay. So by robbing second house, what is the answer I'm getting? By robbing the second house, I'm getting 3 as an answer. And by not robbing the second house, what I'm getting? I'll be getting 1 as an answer. What is the maximum here? 3 will be the maximum. So I'll send 3. Okay. So by robbing the second house, I'm getting 3 as an answer. And by not robbing also, I'm getting the 3 as an answer. So what will be the condition here? What will be the maximum here? 3 only. So I'll send 3 here. Okay. So I'm successfully calculated the answer for here. What will be the maximum by robbing the first house? It will be 4, and by not robbing the first house 3. What will be the maximum here? By robbing the first house only, I'm getting the maximum here. So answer will be 4. Okay. So this is the recursive tree here. So let us observe how we can optimize this solution. Okay, we have to minimize the repeated calls, right? Repeated recursive calls, right? So what are the repeated recursive calls here? Let us visualize here. Okay, so when we want to when we are at a 0, we can go to second and we can go to 1, right? So if we go to second, from second we can go to 4 and we can go to 3. So from 3 we can go to 5. Uh, from 3 we can go to 5 and 4. Here we have come and we have calculated answer for 3, and these two also we have calculated from 4, and for 3 also we calculated and written the answer for 2. For 2, from 2 we have calculated answer and written the answer for 1. Okay, so now we need to calculate for 1 here. Okay, so now we will check whether if one index has been calculated previously. I think no, right? It is not calculated previously, right? So we will check for the one, right? Okay, and let us check for one. So from one, where we can go? We can go to 3 and we can go to 2. So if you observe here, we have already calculated the answer for 3. So here in this case, what we need to do here? If you observe, we have already calculated the answer here, right? We have already calculated the answer here, right? So we don't need to calculate the answer here. So this is a repeated call here. So we will not repeat this call. Why? Because it is already repeated. So in the deep dynamic programming, what we have to do? If the before so what we have to do? Before returning some value, we need to store that value somewhere, right? So if we store that value, whenever we return again to that value, then we can directly return the answer instead of going to another instead of doing that calculation again. Okay, so this is the dynamic programming, right? So here dynamic programming applies here. Why? Because this is the repeated call here. So to ignore the repeated call, we need to store the first we need to store the call of previous call answer, and here we need to ignore that calculation here. Okay, so we have ignored the calculation and we have written the just answer here by storing the previous call answer. So and we have gone to 2 comma 3. So okay, so if you observe 2 comma 3 is also already calculated previously. If you see here 2 comma 3 is also calculated previously. So what we have to do, if we have stored the answer for 2 comma 3 previously, then in this case um, we should have written that answer, right? Instead of calculating this subtree, right? So this is the power of dynamic programming here. So if we store the answer previously for this call, if we would have stored the answer previously for this call, we would have directly called we would have directly written that answer here, right? So ultimate goal is to what is the goal? Ultimate goal is to store the answer at that call, and whenever we return to the call again, and we need to return that value here. Okay. So if you observe here, uh, what is the we have decreased so much of time complexity, right? By decreasing this subtree and by not calculating this subtree, we have decreased so much of time complexity, right? So it was 2 to the power of 100, right? But it is now just going to all the values of array here. That's it. So it is going all the values of array only, right? So it will be big O of n. So from 2 to the power of exponential, from exponential time complexity, we have reduced the time complexity to big O of n. Okay, this is the dynamic programming approach here we need to follow here. So how to apply that dynamic programming approach? Let us see that. Okay, so I hope this dynamic programming illustration you have understood, and here coding the dynamic programming logic here. Okay, so now, so for applying dynamic programming in the recursive solution, we need to have a dynamic programming DP array, right? So what will be the length of a DP array? It will be, so the nums dot length is max will be 100. So our DP length should be 101, right? It should be more than it should be the length plus 1, right? So here in the solve function, what are the parameters are changing? Only I parameter is changing, right? So our DP will be 1D DP only, right? So DP new nums dot nums dot length plus 1, right? Or else we need to take 101 here. Okay, so we will take, let us take 101 here, because as we are going to 4 and 5, right? So we need to take 101 here. Okay, so and we will pass DP here. Okay, and we need to change this parameter. So before calculating the solution, what we need to do, we need to check whether it is present in DP or not. Okay, so and we need to turn out all the values of DP to -1 here. Okay, arrays dot fill DP equal to -1. Okay, so this is how we will be filling DP with -1 here. So before calculating the recursive function here, what we have to do, we need to check whether the answer is present in DP or not. So we will check here. If DP of 5 not equal to -1, then it is present, right? Then it is already calculated. So if it is already calculated, then we can directly return here, right? Instead of calculating the whole subarray again, right? So we will return here DP of I. So, and what we need to do, and before returning, we need to store that value in a DP array, right? So we will store that array. Before returning, we will be storing that array and we will be returning that value. Okay, so this is how we will be turning the recursive solution into a DP solution here. This is how we will be performing the DP operation here. Okay, so let us try to run this solution. So I think I haven't passed the parameters for these cases, and we need to pass the cases here. Okay, and DP, yep, and let us run here. So it is accepted. So let us try to submit here. It is accepted, and this is the DP approach, memorization approach here. Okay, DP of memorization. Okay, so this is it, friends, and thanks for watching the video, and please subscribe to the channel for more type of these problems, and thank you.